Earthquakes and volcanic activity have to be the most exciting phases of geology, at least in my opinion. And the interesting thing about these two phenomena is if you sort of go back in time, there's always been a relationship between the two that have been known for a very, very, very long time. For example, if we went back, even for the days of geology, remember geology didn't come onto the scene until, the mid-1700s. I mean, there were earth scientists before that had an idea what the world was like, because by this time we were already sailing around the world and exploring distant places. And so these people already knew, for example, where most of the volcanism was, and also where the major killer earthquakes were. And they seem to be all associated with the same kinds of places. For example, they knew even then that most of the volcanic activity, the killer volcanoes certainly, and the killer earthquakes were located in a zone around the Pacific Ocean. Now that forever has been referred to as the Ring of Fire, and even today that's where most of your volcanic activity is. Most of the active volcanoes at any one time are located around the Pacific Ocean basin. Well, if you just keep track of where all the potential killer volcanoes are over a period of time, you'll find out that is also a zone of very high incidence of potential killer earthquakes. Well, they knew about that one. Then they knew there was another one. The other one went through the Mediterranean, sort of heading over toward the Himalaya, and that's a zone, of course, of volcanic activity. You've got Mount Vesuvius, Mount Etna, and a number of others. It's also a zone of potential killer earthquakes. We just had a number of them over in Pakistan and places like that. That's part of this zone we're talking about. So they knew about that one. And they also knew about the other one. The other one went down through Indonesia and eventually ended up over the western margin of the Pacific. It's sort of the Pacific Rim kind of thing seemed to tie together with this one. And today, as a matter of fact, there's a volcanic eruption going on today that is the result of eruptions in Indonesia. Well, these are also places of extreme volcanic activity and earthquake activity. And for example, the earthquake that caused a huge wave, we call it tsunami, that had wreaked destruction on Sri Lanka, that was in the Indonesian zone. So they've known about these for a long time. But remember, this is before the days of plate tectonics. They didn't know why they were associated. But the fact that they were, this led geologists for many moons. I'm not sure I can say right up to the time I took geology my first time, but for many moons, this was the reason why they thought one was the cause of the other, because they had this same pattern worldwide. And there were people who argued that a volcanic eruption causes an earthquake to occur. Their argument was the molten rock forces the way to the surface, pushing rocks out of the way, cracking them, breaking them, and an earthquake occurs. Well, there were other people who said, no, that's not the way it works. The way it works is you have this earthquake that breaks things up and allows the molten rock come to the surface. Well, they went back and forth. Turns out, of course, that it isn't a question of cause and effect. The reason why they're associated with each other is because they're both associated with the same thing, zones of subduction. But see, we never knew that until plate tectonics came onto the scene. Well, once plate tectonics came onto the scene, then we had another zone we didn't know about before. We had another zone of active volcanism, which we call, of course, the oceanic ridge. Now, of course, with the rifts too, but the main one is the oceanic ridge. And once we discovered the oceanic ridge, we also discovered it was highly volcanic active. Molten rock was coming to the surface along the summit of the mid-oceanic ridges and creating new oceanic crust. We've talked a lot about that. But the interesting thing is, if you compare that volcanism to the volcanism that occurs along the zones of subduction, that was different. Remember, the volcanism that occurred along the zones of subduction, those were all potential killers. Those eruptions never occurred non-explosively. So that's where your potential killer volcanic eruptions were. Whereas along the oceanic ridges, a good example, of course, being Iceland, you never had that. There was the Hawaiian phase. Remember that? Well, now we understand that one too. It was simply a question of the different kinds of magmas. In one case, you were dealing with an andesitic magma coming to the surface and associated with a zone of subduction. Lots of gas, always going to be explosive eruptions. So there's your potential killers. But over in the other case now, here comes this basaltic magma to the surface. Very little gas by the time it gets there. So you never have an explosive eruption. Again, on Iceland, which would be a typical example of an oceanic ridge. Well, we understand that one. But here's the other one we have to figure out. What we don't know yet is, at this time, before plate tectonics, why is it now that the earthquakes that are associated with the oceanic ridges are very low in intensity? And they are. We're going to talk about Richter scale stuff next time. But these are all very, very low on the Richter scale. We're talking about earthquakes. You might be able to feel them, but no one was ever killed by an earthquake along an oceanic ridge. We're talking, let's say, Iceland, for example. No one was ever killed by an earthquake up there. And why? Why is it that the earthquakes that are associated with the zones of subduction are always potential killers anyway, and those that are associated with the oceanic ridges are not? Well, I think all you have to do now is think about the difference between those two zones. The zone of subduction, we're talking here compressive forces. We're talking about the biggest compressive forces on Earth. You can't get any bigger head-on collision than a zone of subduction. On the other hand, on the oceanic ridge, we're talking about tensional forces. You're talking about pulling rocks apart. Does that have something to do with it? Well, yes, it does, as a matter of fact. Here's all you have to remember. Under compression, rocks are very, very, very strong. Very strong under compression. Very, very weak under tension. For example, you can take a slab of rock and put it down, and you can stack as many rocks on top of that as you want. Picture the highest building you know, big tower, whatever. I don't care how high you build it. The rock on the bottom will withstand the weight of everything you put above. Why? That's non-rotational compression we're talking. That's where rocks are really, really, really strong. On the other hand, you take that same rock and you chuck it up in some kind of a vise thing and try to pull it apart. We're talking tensional forces now. Same rock, but it will break very, very quickly. Why? Rocks under tension are very, very weak. Well, let me give you a little sort of I love trivia, of course, and especially historical trivia. So here's a little bit of historic trivia for you that sort of hopefully will allow you to remember that little thing about rocks being strong under compression, weak under tension. What I want you to do is to imagine the difference now between the architecture of ancient Greece and the architecture of Rome. Okay? All right, architecture of ancient Greece. We're talking now the Acropolis. Up on top of the hill behind Athens, you have the Parthenon. And what is it that characterizes the Parthenon and everything else they built for that matter? Lots and lots and lots of columns. They loved those columns. You ever wonder why they did that? Just think of how much that must have cost to make all those columns. Be great for the column makers, of course, but why did they do that? Well, I think the reason why the Greeks did that is because they never could figure out how to overcome the inherent weakness of rocks under tension. For example, here's what they did. You have a column, and then they span between the columns with a flat layer of rock they call a lintel. Okay, so picture this flat layer of rock now. Note the forces. The forces are rotational compression. The up forces will be the columns underneath the ends of the lintel. The weight of the lintel itself, and everything put above it, of course, is pushing down on the lintel. So note you have rotational compression. So now the lintel now is being subjected to rotational compression. But if you subject something like that to rotational compression, the forces inside are going to be tensional. Rocks are very, very weak under tension. So the problem was, whenever they built these buildings, they found there was a limit as to how far they could get the posts apart. For example, I'm sure that when they built the Parthenon, they would have much been very happy, put a post at each corner and put the roof on. But they couldn't do that because they found out that as you took the post further and further apart, and as that lintel got longer and longer and longer, pretty soon it would fail even under its own weight, let alone whatever you put above, and it fails by tensional forces. Very, very weak. And here's just a little experiment you can do to yourself if you want to prove it. If you take a pencil, for example, and you just hook it between your fingers like that, two hands, and take your thumbs and push down on it. Now, the force I'm adding now, this is rotational compression. Up on the ends, down in the middle, rotational compression. But what's forming inside the pencil, in this case, are tensional forces. So if you do it long enough, the pencil will break, and the points come away from each other. Why did they come away? Because there were tensional forces being developed within it. They never could figure out how to overcome those tensional forces. So as a result, when they built their buildings, they had lots and lots and lots and lots of columns, which you must admit really looks good. I mean, what would the Parthenon look like with 4 posts? It'd be something different again. Okay, so much for the Greeks. Now let's go to the Romans. What characterizes Roman architecture? Well, it's the Roman arch. The Roman arch is what characterizes Roman architecture. And the interesting thing about the Romans, you know, they're given credit for an awful lot of stuff that they really didn't do. What the Romans were really good at were going into some place, sort of taking it over. They were good administrators, but then they would take whatever these other people had and maybe embellish it a little bit, maybe pass it off as their own, but it really wasn't theirs and everybody knew it. But what they did do some things. For example, they invented concrete. And I think that's one of the reasons why the Romans were such good builders. They finally invented a way to stick rocks together, you see. That's pretty important if you want to build a big building like the Colosseum. So anyway, they invented, though, however, the arch. And the secret of the arch is that keystone. The keystone at the top, remember what it is? It's a wedge-shaped rock like that. Now here's what wedges do. What wedges do, if you load them from above, they force the forces out to the sides. I don't care whether it's a keystone in an arch or a chisel. They all work the same way. They direct the forces away from the keystone or the chisel. So here's the point. If you load an arch from above, the keystone throws the forces out to the side. So the contact between the keystone and the first block of the arch, that's non-rotational compression. And then the contact between that block and the next block, that's non-rotational compression. And for the next one, same thing. Finally, we're down to the top of the post. That's non-rotational compression. And of course, the contact with the post or the column and the ground, that's non-rotational compression. So note, in the entire arch from one side to the other, the only forces there are non-rotational compression. Rocks are very, very strong under non-rotational compression. So there's the reason why I don't think there's any limit to how big an arch you can build. But you can thank the Romans then for all the beautiful arch ceilings and dome ceilings around the world and anything that's an arch. I'm thinking of the bridge across the New River Gorge in West Virginia. Well, this thing it's huge, but yet it's very, very strong because it's an arch. Any arch is strong like that because loaded from above, the forces within it are basically non-rotational compression. It was the Romans that figured that one out. Okay, so much for that. No, well, what's the big deal then? Well, what does it mean to be strong and weak? Well, rocks are strong under compression, weak under tension. Okay? What does it really mean, though? Well, let's go back to our discussion now of deformation of things and stuff. Elastic phase, brittle phase, okay? During the elastic phase, you're going to store energy, and you're going to store it up to the elastic limit, and at that point, something's going to break, okay? So let's say something is strong. What does strong really mean? Well, what strong really means, this rock we're talking about, you could start applying any kind of force to it. It will start absorbing the energy and storing the energy up to its elastic limit. But being strong means that the elastic limit now is going to be very, very high. What does that mean? Well, that means during the elastic phase of deformation, you're going to store a lot of energy in this rock during that phase. So finally, when you finally reach the elastic limit and you go beyond and it breaks, if you stored a lot of energy, then you release a lot of energy. On the other hand, if it's something is weak, that means you reach the elastic limit pretty fast. You don't store very much energy before you get there. And when the stuff breaks, the same rock perhaps under tension now, you didn't store much in the elastic phase, which means you're not going to get very much back after the elastic limit is reached. So here's the picture then. We're talking about zones of subduction, for example. We're talking compressive forces of the first order. No place on Earth are you going to have those kind of compressive forces. Enormous amounts of energy can be stored during that collision between those two plates. When it finally breaks and forms those thrust faults or reverse faults that we call a zone of subduction, you've already stored enormous amounts of energy. That energy is released, and as a result, you have a potential killer earthquake. So anytime that you have an earthquake, you hear about it on TV or you read about it in the paper, here's all I'd like you to do. Whip out a map of all the plates. Remember, not many of these placed, but whip out your map and look to see where the earthquake was. And I will absolutely guarantee you it will be along one of those zones of subduction. The earthquakes we just mentioned, the one in Indonesia, the one in Pakistan, those are all zones of subduction we're talking about. That's the reason why. We're talking compressive forces here, storing an awful lot of energy during that compressive phase. How about the oceanic ridge? Or any other rift for that matter? We're talking about pulling the rocks apart. Under tension like that, the rocks are really not very strong at all. They're really pretty weak. So as we pull this rock apart now, we're storing energy during the elastic phase. Remember, elastic phase is always first. And we're storing energy up until the elastic limit. But remember what it means to be weak. Under tension, it means that you're going to reach that elastic limit pretty quick. And when you reach the elastic limit pretty quick, you haven't stored much energy, so as a result, there's not much energy to be released. So as a result, any earthquake that's associated with a divergent margin, we're talking any of the rift zones, rift valleys, and of course the big one, the oceanic ridge, we're talking about an earthquake where you're talking maybe 2 or 3 on the Richter scale, which we get to that. You can just barely feel that. So in other words, there's the reason why we now understand why the earthquakes with those 2 zones are totally different. It's simply the response of materials to stress is all it is. You've already learned all about that. Okay, let's talk about shock waves now. The energy that's released whenever rocks break, they release shock waves. Now, a shock wave is a general term. If it happens to be generated as a result of the movement of a fault, in other words, an earthquake, we call it a seismic wave. A seismic wave is simply a shock wave strictly associated now with a fault movement. All right, kinds of. There are 2 fundamentally different kinds of shock waves. One's called shear. Now, picture this now. In a shear wave, let's say the shear wave was traveling away from you. So that's the direction of propagation now, traveling away from you. What it's doing, whatever it's moving through now, it's moving that material perpendicular to the direction of propagation. For example, the little drawing shows it moving back and forth horizontally and up and down vertically. But remember now, perpendicular is perpendicular. Those are simply 2 perpendicular directions. But in between those, there's a whole mess of other ones. So the idea is that this shock wave goes through, what's happening to the rock or whatever it's going through is going out and in and out and in like that. Moving the stuff perpendicular, that's the important part. So that's the shear wave. Now the compression wave is kind of totally different. In the compression wave, if you can imagine the shock wave moving away from you again, the material it's moving through is moving the stuff back and forth in the direction in which it's going. In other words, it's a back and forth kind of thing. And the best sort of model I've ever seen for that, if you want to sort of picture it, is the old slinky. You know, you take that spring, you take a slinky and put most of the coil in one hand and a few in the other, and let it go. It goes wong, 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 back and forth like that. Well, that would be a typical compression wave. Now, here's a sort of little tidbit trivia, a sideline. The shear waves. The shear waves will only go through solids. Why? Only solids can be sheared or cut, you see. For example, let's say you take a pair of shears, all right, and if you snap them around in the air, really not doing anything, see? And if you put them in a bucket of water and snap them around, well, you're not really doing anything either because you're just making a mess. But if you snap around, put your finger in there, you cut your finger off. Why? They only go through solids. They don't go through liquids and gases. On the other hand, compressive waves can go through anything, solids, liquids, or gases. For example, you're hearing my voice. That means my voice, the shock wave that is being made by my throat here, is traveling across the air to your ear. So it can go through air or a gas. On the other hand, you can hear underwater. Well, that's because these compressive waves can go through liquid too. Or you can put your ear to a railroad track if you want to and listen for the train coming because it goes through solids. So compressive waves can go through any medium whatsoever, whereas the shear waves can only go through solids. Okay, so much for the kind of shock waves now. Now on to 2 words, focus and epicenter. Now, these are 2 words that oftentimes people use synonymously, but they're totally different. So let's picture this now. A big hunk of the earth crust, a big cube, and now I have on the cube, picture the focus down below inside this cube someplace. And the epicenter now is on the surface. Now, let's go back to the focus. Significance of the focus. That's where the earthquake occurred. that's where the fault movement occurred. That's where the energy was released. So the secret of the focus is that's where the energy is released during an earthquake. The epicenter, by definition now, is the point on the surface of the ground immediately above the focus. Now note, if the focus is on the surface, like remember most faults are, then they would both be in the same place, but that's only fortuitous. But the point is that the focus could be anywhere in depth, within limits, of course. For example, let's say we made a chart with depth versus the number of earthquakes or the number of faults. And if you do that, remember we said most of the faulting was in the first 40 miles of the Earth's crust, from 40 miles, from the surface down to 40 miles, the Earth's crust. Those are called shallow focus earthquakes within that first 40 miles. And let's see, 75% of all the earthquakes are in that zone. Why? That's where the rocks are most brittle. That's what we're talking about here, breaking, you see. And then from about 40 miles down to about 200, 250 miles, note the number of earthquakes drops off really fast, only about 20%. Why? The rocks are becoming more plastic, you see. They're starting to flow rather than break. Well, those are called intermediate focus earthquakes. And if you go below 250, down to about maybe 450, there's only about 5% of earthquakes down to, they call them deep focus earthquakes. You don't have many because now the rocks are really, they're responding mostly by plastic flow is what they're doing. They're folding perhaps, but they're not breaking. Therefore, if they don't break, you can't have a fault. Well, once you go below 450, there are no earthquakes. Why? Because the rocks are totally plastic. And again, if it's acting like a plastic, it's flowing. If it doesn't break, it's not going to give off one. So anyway, there's a distribution of your earthquakes with depth. Now, let's talk about different kinds of seismic waves. Let's go back to that focus business. At the focus of the earthquake, what's happening now? We'll picture this thing down at depth. It's sort of a general picture. Okay, so here's the focus at some depth. Who cares how far? But this is where the energy is going to be released now. The energy is released from the focus in the form of what we call body waves. Now the body waves are both shear and compression. Okay, the shear waves are designated S waves. The compression waves are designated P. Okay, so you have the S's and the P's. These are both moving away as body waves. Now here's the important thing. In terms of earth movement, rock movement, the amount of energy that is being used to actually move the rocks as the body waves go through the body of the earth, you see, that's why they're called body waves, very, very, very little. My seismic guru tells me that the total amount of rock movement is on the order like maybe a fraction of a millimeter, so it's almost nothing. So note the point is, of all the energy being released at the focus, very little is going to be wasted, if you will, moving rocks around. What's it going to be used for? Well, for anything else the thing wants to do. For example, moving itself. And as a result of having all that energy, it turns out these body waves go through the earth very, very fast. Again, my seismic guru tells me that a body wave can travel from one side of the earth completely through the center to the other side. Remember now, that's 8,000 miles, and it can do it in something like 20 minutes. Well, just calculate that out. If I'm right, it comes out to something like what is that, 24,000 miles an hour. So anyway, that's pretty fast, okay? Pretty fast. Now, on the other hand, what's left with the rest of the energy? Even that we don't use an awful lot of. So now, what happens to that energy? Note that the epicenter, directly above the focus, note the significance of that is. Being directly above the focus, that means that's the shortest distance that the body waves have to travel to get to the surface. So it means that's where the most energy is going to be remaining in the body waves. And once the body waves get to the surface at the epicenter, it transfers the energy over to the surface now of the Earth and generates what we're going to call surface waves. So the idea is now the maximum energy is at the focus, at the epicenter. And that's one of the whole things about the epicenter. You always hear they're always looking for it. Well, the reason why they're looking for it is that's the point where the energy is the greatest. Now, as you go out in all directions from the epicenter, what's going to happen is the energy is going to drop off. Why? Well, it's doing things like moving the land around and knocking buildings down and scaring you and all that kind of stuff. So it's using energy up. So the idea of the epicenter, that's where the energy is going to be greatest, but as you go out in all directions, it's going to die off, and we'll talk about that next time when we talk about damage. But anyway, let's go back to the epicenter now. What it does at the epicenter, the energy is transferred to the surface and creates surface waves. Surface waves now. Now the surface waves are totally different from the body waves. The main difference between them is the amplitude of the movement, whereas the body waves move the rocks almost nothing. Okay, we're talking now about fairly large movements of the rocks. So large, as a matter of fact, we'll talk about this next time, but so large that in some cases you can actually see the surface wave moving across the surface of the earth. Now you have to have a pretty good amplitude to see that. So anyway, that's one of the big differences. You have very high amplitudes. Now, high amplitudes, you're burning up an awful lot of energy, see, moving rocks around, and so those are going to die off pretty fast. So as you go away from the epicenter, once again, the amplitudes are going to die off. So the maximum amplitude is going to be at the epicenter, and then it's going to die off as you go away, and that's going to affect our discussions for next time. But what's the big difference between the surface waves? There are two kinds, Love and Rayleigh. And here's the difference between them. The Love wave is a shear wave, meaning the rocks are being moved perpendicular to the direction of propagation. So let's picture now that the Love wave is moving away from you across the surface of the earth. It is a shear wave, so you're going to be moving the rocks back and forth perpendicular to the direction of propagation, but only in the horizontal plane. See, not any of those others, only in the horizontal plane. So as the Love wave goes across the surface of the earth is being moved back and forth, perpendicular to the direction in which the Love wave is going. Now, on the other hand, the Rayleigh wave is really the cool one. The Rayleigh wave, what it is, it's a combination of the vertical component of shear, up and down, okay, vertical component of shear, plus that to and fro motion of compression. So if you picture this one now, the motion of the earth is going to be forward and up, backward and down, forward and up, backward and down. So it's going to be a crazy rolling motion like that. So both of those are going across the surface of the earth simultaneously in all directions. Now, one of the things we're going to talk about in the next lecture is damage, but just sort of to introduce it at this point. Question: of those two kinds of surface waves, gut feeling, which one do you think would cause the most damage? Well, I'll tell you the one I answered when I was a student and asked that question. Of course, now, I always picked the wrong answer, but anyway, that's another story. I picked the Rayleigh wave. Why? It just seemed to me that this shock wave going across the earth, just undulating the ground like that, up and down like that, wow, that must be wild. I mean, it's going to tear buildings down and all kinds of stuff. Well, this goes to show you that isn't the right answer. The engineers tell us the big damager in earthquakes, of course, I mean, you're going to damage with the Rayleigh waves too, but the bigger of the two, the biggest damage is caused by the Love waves. Now picture them, they're going back and forth, back and forth. That doesn't seem to be any big deal, but here's the thing. I think you can prove it to yourself with a very, very simple little experiment. Take a stack of dominoes and put it in your hand. Now this stack of dominoes represents a tall building, a smokestack, I don't care what it is. It's some kind of a structure. Now what you're going to do, if you're very careful, we're going to reproduce the Rayleigh motion. Remember the to and fro, that stuff? Very carefully, if you just got your hand and try to follow that sort of rotating, undulating motion, if you're very careful, you can get to the end and the dominoes are still there. In other words, they didn't come down. In other words, the destruction there was minimal. Okay. On the other hand, let's say you take the Love motion now. If that's the direction to say it's going away from you, remember now, it's moving it back and forth. Same stack of dominoes now. The difference is now the earth is moving to one side, and then back to the other side again, back and forth like that. And here's the picture now. Picture the earth and the stack of dominoes now going sideways, and then it's going to get to the end of the run, and then the earth turns around and goes back the other way. But nobody told the stack of dominoes. Remember inertia? When in motion tends to keep you in motion. So here's this stack of dominoes, which is your building or your smokestack. It's going in this direction. When the earth turns around and goes back the other way, the domino stack keeps going in that direction and falls down. So there's the reason why that most of the damage is the result of the Love wave. It's this It's that turnaround at the end that really kills you. It isn't the trip between the ends, it's that turnaround at the ends. So combining those two then, that's where the damage comes from. But when we get around to talking about damage due to earthquakes, just keep in mind that the Rayleigh wave, although got to do something, it's still a rolling motion, you see, but between the two, the love wave does the greater amount of damage. But we'll talk about that next time when we get into the discussion of damage.